All right, this is video part 2 of the homework help for Unit 12. We're going to start with question 7 in this one, but I wanted to backtrack on a couple of things just to make sure that you've seen this. So I am going to add a couple of notes if you want to take them or just kind of pay attention. So the first 6 questions, we were dealing with forces within and between atoms and molecules or formula units. So we talked about intermolecular forces versus and I didn't mention this term, intramolecular forces. Intermolecular is between molecules. All right. So two separate molecules, such as two different water molecules, and how they would interact. All right. Usually, an intermolecular force is represented by a dashed or dotted line. An intramolecular is within. This is an actual chemical bond. All right. So when we're talking about intra, it's the actual bond. So we have hydrogen bonded to oxygen here, hydrogen bonded to oxygen. All right. So that is intramolecular. Inter is going to be this interaction in between here. And just because we didn't have this choice on any of the questions earlier, this interaction right here, just so you can see, this interaction between oxygen and hydrogen would be a hydrogen bond, which is kind of a misnomer because it's not an actual bond, it's an IMF, an intermolecular force. All right, so just going through here real quick, I want to look through these. Intermolecular is between molecules, is not as strong, they're weak. Intermolecular forces are responsible for things such as protein structure, DNA, taste, existence of liquid solids and gases. And this is where we're going with this today, is getting into this. How does this affect it? Intramolecular forces are the attractive forces within a molecule. That's the chemical bonds. That's the big deal there. Bond between atoms and ions. Very hard to break. They're very strong. Two main types. Ion-ion, which is an ionic bond, or a covalent bond sharing electrons. All right, so kind of moving forward in this, getting into the things, how do we determine an intermolecular force? So I'm going to zoom out for a minute just so that you can see this whole picture. All right, so determining an intermolecular force is in a sample. There's a few things that we can ask. We have to ask some questions, and then we can follow this flow chart. So what we have to look at first, the particles that are interacting, are they atoms, molecules, or ions? All right. If there are only ions present, then it's ionic bonding because the positive and negative are going to attract each other. And this is called ion dipole forces. All right. This is all related to ionic bonding. All right. Now, getting into this other side, is it molecules present? So if there are no ions present, then it's got to be a molecule. So the next question that we ask, is it polar or nonpolar? All right. If it is nonpolar, molecules will only have dispersion forces, which we call London dispersion, or LDs. All right. If it happens to be a polar molecule, we can have dipole-dipole forces, and then under there, if not only can we have dipole-dipole forces, if hydrogen is bonded to nitrogen, oxygen, or fluorine, then we can have hydrogen bonding as well. If ions are not present and it's a polar and a nonpolar molecule, then we have what's called dipole-induced dipole forces, which is very similar to dipole-dipole. A lot of textbooks don't even distinguish. All right, so moving on. This is one factor that's going to affect the phase of matter. So really, factors affecting phase. One of these is called vapor pressure. how likely, which is kind of is how likely will it be a gas? All right. So one thing that affects vapor pressure is temperature. An increase in temperature, um, in, increasing temperature increases energy. Increase temperature increases energy. So the higher the temperature, the higher the pressure. So as the temperature increases, the fraction of molecules with enough energy to um, enter the vapor phase increases and the vapor pressure increases. So don't do this because this is a very high pressure situation. It can cause problems. But if you had a sealed pot, like like a lot of y'all might have, parents or whoever might have an Instapot, which is a pressure cooker. As the temperature increases in there, so does the pressure. Higher temperature equals higher pressure. Um, we produce that vapor at that higher pressure. All right. So enough energy to enter the vapor phase, and it increases because we have so much more vapor in there. The pressure on the sides of the container increases as well. Higher temperature equals higher pressure. All right. If something has weaker intermolecular forces, the more easily those particles enter the vapor phase. So it will have a higher vapor pressure. So a weak IMF equals higher pressure. So nonpolar molecules are more likely to be a gas than polar molecules. Now, that's all things being considered that everything else is the same size molecule, things like that. Polarity will affect your vapor pressure. The higher the vapor pressure, the more likely it is to be a gas. All right. So let's look at this. Let's look at this diagram in that. Vapor. We already stated this. Vapor pressure increases as temperature increases. Vapor pressure decreases as the strength of intermolecular forces increases. So um, we have these molecules here: ethanol, water, and diethyl ether. All right. Um, water is a molecule that looks like this. It has hydrogen bonding. Which is very strong IMF. All right. So what I want you to notice about this one, um, these numbers are vapor pressure. Um, these numbers are temperature. So we're going to look at the same temperature here at 20 degrees. Notice how low the vapor pressure is. So that means that this water is likely to be a liquid. That's why water kind of maintains that. So if you kind of look up here, water doesn't become a gas until this point. It boils. This is the boiling point of water at 100 degrees Celsius and 760, which is 1 atmosphere of pressure or standard pressure. All right. So what we see here we have to raise the temperature of water to 100 degrees Celsius at 760 psi in order for it to vaporize. All right, there will be some vaporization that's happening all along here, but very, very small amount. The only thing that happens here is evaporation will occur. Some molecules will escape into the air, but then at this point, it completely vaporizes. It goes from a liquid to a gas. Now, looking at ethanol, ethanol is a 2-carbon structure that has hydrogens around one side, and then it's going to have an oxygen and a hydrogen like this. Something like this. All right. This is a very simplified version of it, but this is ethanol. Notice that it is a polar molecule. All right. It's a polar molecule, but it doesn't necessarily have to go under hydrogen bonding as much as this, because here you only have the oxygens and hydrogens, but in this one you also have carbon, so you're not always going to likely form a hydrogen bond on these. So this one's a polar molecule. Vapor pressure is a little bit higher, meaning it has these points where at 20 degrees Celsius, the vapor pressure is like around 50. At 75 degrees, 78.5 degrees Celsius, we're at 760. So this one gets to that point at a much lower temperature, so boiling point is going to be lower. Also notice that the size of the molecule is bigger. And now this diethyl ether, I'm going to do this over here on the side, but basically we have this structure like this where we've got hydrogens all the way surrounding it. We got this oxygen in the middle that's forming this long chain. And so it's a very, very big molecule, but this molecule is nonpolar. All right. So notice that the molecule's nonpolar, so it's much easier to get it to become a gas. In fact, it becomes a gas at 34.5. That's why we usually associate ethers as things that have a strong odor. They are very volatile, that's another word, meaning they're likely to become a gas. So one of the factors is polarity. The higher the polarity, the more likely it is to be a liquid or a solid. The lower the polarity, the more likely it is to be a gas. Another factor is going to jump in there is the size of the molecule or the mass of the molecule, but we'll get into that a little bit later. All right. Liquid properties affected by intermolecular forces. So boiling point is affected by it. That is going to be dealing with vapor pressure and all of that. Viscosity, how thick the liquid is or how sticky the liquid is to itself. Surface tension and capillary action. So I'm going to go through these real quick. You can go back and forth. So dealing with surface tension and capillary action, we have these concepts of cohesion and adhesion. Intermolecular forces that bind similar molecules to one another are called cohesive forces. All right, this is the idea that a molecule wants to stick to molecules stick to like molecules. So the idea of something wants to stick more to itself. Intermolecular forces that bind a substance to a surface is called adhesive forces. So think about like tapes and glues are called adhesives. So they allow something to stick to something else. So this would be the idea that the molecule wants to stick to the container. All right. All right. These forces are important in capillary action. So if you have something that wants to stick to the container and you stick it in, I have a cup of water here. And then I take this little small straw, and if you've ever done this with a plastic straw like at McDonald's or something like that, or you have a clear glass and something like Coke or something here, you stick a straw in there. If you notice when you stick the straw in there, you're going to see the level of the Coke or the level of the liquid draws up into the straw a little bit. That's called capillary action, that drawing up in there. And then that has to do with adhesive forces. The idea that these molecules want to stick to the side of the container. Now, another thing that happens in this is when it draws up, you can have two different shapes. If the shape is what we call a meniscus, think about when we were reading graduated cylinders that we say read the bottom of the meniscus. So if it curves like this, if it's a concave shape, then it has to do with adhesive forces. All right. If it's a convex, that means the molecules of the substance want to stick more to each other, so that is cohesive. All right. Cohesive attracts the liquid to itself. Adhesive attracts the liquid to the container. All right. So going into phase change here, all right, energy of the system. So if we have a certain liquid, or let's look at this, and this is kind of that phase change diagram that I gave you earlier. So if we start here at the solid and we want to go to a liquid, we have to add some energy to the system. If we add enough energy at one time, we can go straight from the solid to a gas. And then, if we're at liquid and we add a little more energy, we can vaporize, and then we can have condensation if we remove the energy, freezing, or if we remove enough energy at one time, we can have deposition. We can also affect this with pressure. So conversion from one state of matter to another is called phase change. Either energy is added or released in a phase change. Phase changes include melting and freezing, vaporizing, condensing, sublimating, and depositing. All right. We'll get to that another day. All right. So let's get back to our problems. Which of the following is predicted to have the lowest boiling point? So in order to do this, I'm going to go ahead and draw the molecules. So we have I2. So that's iodine bonded to iodine. All right. So dealing with these, we have to look at the molecules by structure. We have to look at them by size and things like that as well. So which of the following of these will have the lowest boiling point? So another way of asking that is which one is going to boil at the lowest temperature? Which one is most likely to be a gas? Well, first thing that we can look at is when we look at these, all 5 of these particles are non-polar. All right. The next thing that we have to look at, which one of the, looking at these, which one is the smallest molecule? Which one has the lowest mass? So we need to look at mass as well with this. Iodine, even though there's only 2 of them here, iodine's a pretty heavy molecule because iodine's pretty low on the periodic table, so it's going to have a lot of protons in it. Carbon and chlorine are pretty small. Carbon and sulfur in general are pretty small. When you compare carbon tetrachloride versus carbon tetrabromide, bromine's a heavier element than chlorine, and same thing. Now fluorine's much lighter, but sulfur's heavier than carbon. So what we have to see is also look at this as a very large structure. There's a lot of surface area on there, so there's a lot of space for it to have high. Even though all of them will only experience London dispersion, there's a lot of surface area on this one, so it's going to have a high IMF, a lot of electrons. Same thing with these two, high IMF, high IMF. So what we really need to get to is between A and B on these, which one is going to be the best. And it's going to deal with two things, the mass and the surface area. All right. So when you're looking at this one, I'm going to narrow it down to these two choices. And so the other factor that affects boiling point, if it higher mass, higher molar mass, is higher boiling point. Lower molar mass is lower boiling point. Another thing to state is higher IMF, higher boiling point. So that has to do with surface area. If they're all the same type of intermolecular force, which all of these are London dispersion, they all exhibit the same kind of force, but the bigger the molecule here, the higher the IMF. The smaller the molecule, the lower. All right. Now, this is a smaller molecule, but is it a smaller molecule mass-wise? And that's what you need to check out. So look at A and B for those. All right. Which property typically indicates strong intermolecular forces that are present in a liquid? Low heat of vaporization, low critical temperature, low vapor pressure, low boiling point, low melting point. Remember that strong IMFs equals low VP. Now, let's go back a couple of pages and check that out just to remind you. So earlier, whenever I was doing just the notes part, we talked about this one. It said a weaker intermolecular force would be a higher vapor pressure. So weak force equals high VP. So therefore, a strong force equals low VP. All right. So that brings us back to what we had here. Going back, question number 8, which property tends to indicate strong intermolecular forces? So we're looking for strong intermolecular force is going to have a low vapor pressure. That also means that it will have a low boiling point, things like that. So you got to remember that as well. There might be more than one, but there's a best answer on this one. All right, which term is a measure of the resistance of flow of a liquid? All right, so remember, adhesion talks about sticking to a surface. Capillary action is basically ability to go up a tube. Cohesion sticks to itself. Viscosity talks about how easy something will flow. So like syrup has high viscosity. And something like water has low viscosity. All right, surface tension is if has to do with cohesion, molecules sticking to themselves and allowing things to stay on top of the surface and not break surface. Good videos to watch for surface tension is like whenever they bring a water balloon in space and pop it, and how it makes that globule that just kind of floats around in a low gravity environment, things like that. So moving on. Number 10, which best explains why a meniscus in a mercury glass is convex? So remember that water makes a meniscus that goes down, and mercury makes a meniscus that goes up. So it has to do with adhesion and cohesion. So you need to see which one is going to be the one that makes it back. So if you need to go back a couple of slides and pause it and look at that picture, do that. All right. Which of the following properties does not impact the vapor pressure of a particle of liquid? So remember the things that affect vapor pressure. Vapor pressure is affected by temperature and IMF. All right. So hydrogen bonding is an IMF. Temperature, talked about. Surface tension has to do with IMFs. The volume is just an amount. Viscosity has to do with IMFs. So go from there. Which of the following substances would have the highest vapor pressure? So high vapor pressure means weak IMF. All right. So because they're all at the same temperature, we're only looking at the IMF on this. So we need to look at it. All right. So, and then it's going to be easy enough. So we want to have the one with the highest vapor pressure. So we want to have the one that has the lowest boiling point. All right. So let's look at these. Propanols 97 and 100. Those are higher than this one. So I'm going to say that acetone is it because it has the lowest boiling point. So the statement I'll make on this, high vapor pressure equals low boiling point. Kind of answered that question. I didn't mean to answer the question. Ammonia and hydrogen fluoride both have unusually high boiling points due to, all right, so hydrogen fluoride and ammonia. What do they have in common? It's going to deal with a particular IMF. What type of intermolecular forces can both of those exhibit? Which of the following exhibits dipole-dipole intermolecular forces? So it needs to be polar, and it cannot have nitrogen, oxygen, or hydrogen attached. Nitrogen, oxygen, or fluorine attached to a hydrogen. So boron BF3 looks like this. And I'm not going to fill in the dots around it. CO2 looks like this. And that should be a straight line, not kind of bent like that. NH3 looks like this. Br2 looks like that. And CF4 looks like that. That one's a good question, because looking at these, from what I've drawn, all five of them, 2, 3, 4, 5, all five of them are nonpolar. So which one is polar? The only one that's polar is NH3, but it should exhibit hydrogen bonding, but that, it can also do that as well. So all right, number 15. Which of the following substances would not exhibit hydrogen bonding? So again, you have to look at the structures. All right, so 4 of these can exhibit hydrogen bonding and 1 of them cannot. So what you need to kind of look at is which one doesn't meet the criteria for hydrogen bonding. Number 16, dispersion forces would be weakest in which of the following substances? So I'll give you this statement. The greater the number of electrons, the greater the NF. So in this case, the way it's reading, we're looking for the one with the fewest electrons, total. And that's total number of electrons. All right, which of the following phase changes would be exothermic? All right, so I'm going to stop here. This is going to be part 3, is where we're going to start here at number 17.